All right, now I'd like to talk to you about conservation of angular momentum. And conservation of angular momentum occurs where the impulse is equal to 0. So that if the integral of mdt, if there are no angular impulses, no tangential impulses, if that's equal to 0, then my beginning momentum equals my ending momentum, or my beginning MVR is equal to my ending MVR. In our previous work, or previous page here, where R was equal to the same, or R1 was equal to R2, then velocity would be the same, and obviously we haven't really accomplished very much. But where this concept comes into play and is really valuable is when R is not changing. So let's look at this first piece here, where we have an mv times the distance r, and we're rotating in this kind of direction here. Then my ending condition would be mvr2. So if I've left the string out, I've got a different r. Obviously, I can calculate a different v at the end of that, and that comes in pretty handy. Next thing to keep in mind, however, is that only the tangential velocity, or only the tangential component of the velocity matters. So that if you're letting the string out suddenly, you may be, and then you stop, then obviously that condition applies where R2 is now a constant. But if R2 is not a constant, in other words, if there's an R dot, if it's slowly being let out and the string is slowly getting longer, and if I have a R dot, I'd have a velocity in the R direction. Again, for angular momentum, only the tangential component counts. Only the tangential component means anything from angular momentum. So my beginning angular momentum would be mvr1, that tangential component here. And then my ending angular momentum would be mvr, and only the tangential component makes sense. However, that radial component does come into play with some of our other problems. So that if you had and energy is where we'd use that r, the velocity in the r direction. But if we looked at our beginning energy here, I would have a 1/2 mv squared. And again, only the tangential component counts, or I'd only have the tangential component at this point, but I'd have a 1/2 mv squared if I'm in the horizontal plane. My ending condition, I would have, if I had a velocity in the radial direction and a velocity in the tangential direction, both of those pieces would contribute to my total energy, such that if I take the vector sum of those two pieces and I get v magnitude, that is the component that counts for energy, such that I have 1/2 mv squared here with just tangential, and in this case I'd have 1/2 mv squared of v magnitude, or v total, for my kinetic energy. All right, so that concept can be used pretty handily. Okay, let's look at a little problem here, and let's just see what conservation of momentum can do for us here. So we have a ball at the end of this string, and it says that it's going at an initial speed of 6 feet per second. The initial radius, or the initial distance, is 3 feet. So and then we're pulling it down at a rate of 2 feet per second. We want to find the speed when r is equal to 2 feet. Well, we're starting at 3 feet, so once r is equal to 2 feet, we can easily see from angular momentum that mvr1 is equal to mvr2. The mass in this case is the same, so those cancel out. So I have velocity at the beginning of 6, the radius at the beginning is 3, and velocity at the end is what we're looking for, and the radius is 2, so velocity tangential at condition 2 out here is going to be 9. All right. Then the next question says, how much work is being done to pull down the cord? Well, work is force times distance, but we don't know, and we can find out the distance that we moved. We went 3 feet, and we went now down to 2 feet, but we don't know the force that it's taking to do that. And besides, the force is changing, so it's not a constant force because of the way that works. So I can't use my regular work equations for that. But I can look at conservation of energy, 1/2 mv squared, pretty handily. So when we get out to here, notice that there's going to be a tangential speed and there's a radial speed. The radial speed is given by this guy right here. So the total speed is this vector sum right there, and I've calculated the total speed. I've got a radial speed of 2. I've got a tangential speed of 9, so my total speed is 9.219. That is the v total. Now my kinetic energy is conserved, so I have 1/2 mv squared here, and then I have 1/2 mv squared there, and the difference will be the work that is required to make that happen. So I have 1/2, actually energy is, I guess technically it's not conserved because I am doing some work here to increase the kinetic energy. So I have a beginning kinetic energy plus whatever work I put into it gives me my ending kinetic energy. So I can find the difference there, and I get 3 foot-pounds of work. So in this case, we have a ball at the end of a string, and it's being pulled. It's rotating around in the horizontal plane. This is vertical, so the horizontal plane is going out like this, and it's being pulled up through the hole here so that at a future time it has a new speed and a new height and a new radius. So let's first talk about the radius about which it's rotating. If you recall from previous kind of problems, we know that this is the radius 1. It's actually rotating about that point. I didn't draw that very well, but it's really rotating about this point. That's the radius. It's not really rotating about that point up there. Similarly, then this guy at condition 2 is rotating about that point, isn't it? All right, so then we can draw two-dimensional pictures of condition 1 and condition 2. So I've done that here, and we know that again from work of previous problems, kind of similar, that we know that there's a tension in the cable, and if there's a theta right there, we know that we have 2 components of tension. So I'll say that is T1 sine of theta 1. This one here is T2 sine of theta 2, and we got an mg coming down. Same thing here, T2, so I got T2 sine of theta 2, mg, and T2 sine of theta 2. All right, so those are the pieces of the forces. From the geometry, we know we can find this theta here as that theta 1. Since that's given here, we got a 3-foot-long string, 2 foot long there, so I can say theta 1 is equal to sine minus 1 of 2 over 3. That's one equation that we might want to use. Then also from the geometry, if we're looking for the 2 radii, we can say that R1 is equal to, in this case we have a 3-foot-long string, so I'll say that it is 3 cosine of theta. And over here, R2 is equal to, in this case I got a 1.5 length string, so 1.5 cosine of theta 2. Some of these things you're going to have to work through. Alright, so those are the things we know from the geometry. Next thing to do is recognize that, that this is an NT problem as well as a conservation of momentum problem. So let's write our NT assumptions here. If I sum the forces in the B direction, which is this direction, and I know that those are going to be equal to 0 because it's steady state at the 2 states. So steady state in this case, then I pull the string, now it's steady state again. So that says that at each condition, some of the forces in the B is equal to 0. So I have T sine of theta 1 minus mg equals 0. So there's one equation. Same thing over here. This is T1. So T2 sine theta 2 minus mg equals 0. That's condition 2. And also I know that the sum of the forces in the normal direction equals mass times acceleration in the normal. So I can say T1 cosine theta. This is the only force I have. Oops, I wrote this wrong. I have signs on both of these things. This is crazy. That's actually a cosine. Alright. Sometimes I talk more than I think. But anyway, let's put those both as cosines because that makes more sense. Alright, so T1 cosine of theta is going to be equal to mv squared over rho. And my rho is my r, so that gives me another equation. And over here, I get the same thing. Got that cosine component. T2 cosine of theta 2 is equal to mv squared over its new rho. And that rho down there on the bottom is going to be equal to R2. V here is going to be equal to V1 and V2. Those are my two conditions. So I think I've got kind of close to enough equations to be able to solve for my unknown. As basically our unknown is determine the speed. But you'll find that working through this, you need one more equation, and that's going to be the conservation of momentum equation, and that's going to be the mvr1 is going to be equal to mv2r2. And that is the last equation you'll need to be able to solve for the speed. That's what we're looking for. V2 is what we're looking for. All right, I hope this helps you get set up for your homework and your understanding.